Beneath the golden haze of Saturn's rings lies a world unlike anything we've ever known. Titan, a moon shrouded in mystery and potential. Imagine a place where rivers and lakes aren't filled with water, but liquid methane, and where clouds drift through an atmosphere that could contain the ingredients for life. Titan isn't just another distant celestial body. It's a time capsule, offering a glimpse into what Earth might have looked like billions of years ago. But here's the real question. How do we, with our current technology, even begin to explore such an alien world? Today, we're diving into the groundbreaking technologies that are turning the dream of exploring Titan into a tangible reality. From robotic submarines gliding through methane seas to flying drones soaring over icy landscapes, these advancements are pushing the boundaries of what humanity can achieve. So, what exactly makes Titan so irresistible to scientists, and how are we overcoming the challenges of exploring such a harsh and distant environment? Let's find out. Titan is quite simply one of the most fascinating places in the solar system. Picture this, a moon larger than the planet Mercury, wrapped in a dense, golden haze of nitrogen-rich atmosphere. It's the only moon we know of with a thick, Earth-like atmosphere, so thick, in fact, that standing on Titan wouldn't require a bulky spacesuit, just an oxygen mask and protection from the frigid cold. Now imagine looking out across the landscape to see rivers, lakes, and seas dotting the surface, not filled with water but with liquid methane and ethane. Beneath its icy crust, scientists believe there might even be a subsurface ocean of water, potentially harboring the conditions for life, and this is what makes Titan so extraordinary. It's a world that mirrors key aspects of early Earth, giving us the rare opportunity to peer into our planet's distant past while asking one of humanity's most profound questions: are we alone in the universe? What makes Titan an unparalleled scientific target is its potential for prebiotic chemistry. The moon's surface and atmosphere are rich in organic molecules, the same basic building blocks that led to life on Earth billions of years ago. When sunlight interacts with the methane in Titan's atmosphere, it sparks chemical reactions that create complex hydrocarbons, some of which drift downward to the surface. Scientists suspect that these reactions could mimic the processes that kick-started life on our planet. Essentially, Titan may be conducting a natural experiment on how life could arise from non-living materials. And even if no life exists on Titan today, studying its environment could help us understand what to look for as we search for life beyond Earth. But Titan isn't just about astrobiology. It also holds clues to understanding planetary evolution and climate systems. Its resemblance to a frozen early Earth makes it a natural laboratory for investigating how atmospheres interact with surfaces, how organic chemistry behaves in extreme conditions, and how planetary bodies evolve over time. For example, studying the hydrological cycle on Titan, a cycle involving methane rather than water, could give us new insights into atmospheric processes that aren't limited to our own planet. It's like discovering an alternate version of reality, where similar natural laws create wildly different outcomes. However, exploring Titan comes with some monumental challenges. For starters, the moon is enveloped in temperatures that plunge to an astonishing -290 degrees Fahrenheit. That's cold enough to freeze most materials solid, turning the rigid terrain into an icy expanse that's as captivating as it is unforgiving. The thick, smoggy atmosphere that makes Titan so enticing also hides its surface from view, making navigation and landing incredibly tricky. And then there's the issue of distance. Titan is nearly 1 billion miles away from Earth, meaning spacecraft face years-long journeys just to reach its orbit. Once there, they need to operate in an environment unlike anything we've ever encountered. a landscape of methane seas, ice volcanoes, and a gravity that's about 1/7 of Earth's. These challenges are precisely why Titan demands the most innovative technologies we can imagine. It's a testbed for pushing the limits of exploration, requiring solutions that can withstand extreme temperatures, navigate through thick atmospheres, and adapt to unpredictable terrain. Moving forward, we'll look at the cutting-edge tools humanity is developing to meet these challenges head-on. From robotic submarines designed to explore its methane lakes to aerial drones capable of mapping its hidden surface. Each of these technologies not only brings us closer to uncovering Titan's secrets, but also advances our ability to explore other worlds far beyond our own. Exploring Titan is like preparing for the ultimate endurance test in one of the most extreme environments imaginable. While its thick atmosphere, vast methane lakes, and icy surface make it a fascinating destination for scientists, these very features also present some of the most daunting challenges ever faced in planetary exploration. Overcoming these obstacles requires not only cutting-edge technology, but also a new way of thinking about how we explore worlds vastly different from our own. Let's start with Titan's atmosphere. On one hand, it's incredibly intriguing. It's 4 times denser than Earth's atmosphere and extends high above the surface, creating a world shrouded in eternal orange haze. But this density doesn't just limit visibility, it also complicates landing missions. Traditional descent methods like parachutes behave differently in Titan's thick skies. A spacecraft descending through its atmosphere experiences resistance unlike anything in Earth's thinner air, making it critical to design landing systems that can handle this unique aerodynamic challenge. Adding to the complexity, Titan's gravity is only 1/7 that of Earth, meaning traditional landing protocols need to be completely reimagined to ensure stability. And then there's the cold. Titan's surface temperature hovers around a bone-chilling -290 degrees Fahrenheit. At these temperatures, most materials behave very differently. Plastics become brittle, metals contract and weaken, and even basic electronics risk failure. Engineers must develop systems capable of withstanding such extreme conditions, incorporating specialized materials that remain durable and functional in near cryogenic environments. For instance, batteries, a critical power source for any mission, must be insulated or redesigned entirely to operate in such frigid conditions, where traditional chemical reactions required for power generation can grind to a halt. Every component, from cameras to communication systems, must be rigorously tested for long-term survival in an icy world, but the challenges don't stop there. Titan's surface is unlike anything we've seen before. While Earth's explorers deal with terrain like deserts or forests, Titan offers a radically alien landscape. Lakes and seas of liquid methane and ethane dominate the surface, bordered by solid terrain covered in organic, rich ice. This icy crust can be both rigid and unpredictable, with potential cryovulcanos, volcanoes that spew water or ammonia instead of lava, adding further complexity. Imagine trying to design a rover that can traverse a surface where the ground might be rock-hard ice in one area and slushy methane-soaked terrain in another. Every exploration vehicle must be able to adapt to a variety of conditions, all while transmitting valuable data back to Earth across nearly 1 billion miles of space. Even the lakes themselves pose unique challenges. Unlike Earth's lakes composed of water, Titan's lakes are made of liquid hydrocarbons, a totally different chemical environment. Any robotic explorer sent to dive beneath their surface must be able to withstand the chemical and thermal properties of liquid methane while conducting experiments and gathering data. This requires not only durable materials but also specialized sensors capable of functioning in an environment humans have never encountered before. Communication also becomes a significant hurdle. Because of the vast distance between Titan and Earth, signals take more than an hour to travel one way. This delay rules out real-time mission control, meaning spacecraft and robotic explorers must be semi-autonomous, capable of making decisions without waiting for instructions. These robots need advanced artificial intelligence to navigate, conduct experiments, and adapt to unexpected conditions, all without human intervention for extended periods. In many ways, Titan's challenges are a double-edged sword. On one side, its dense atmosphere and frozen environment make it an incredibly difficult place to explore. But on the other, these challenges are also what makes Titan so exciting. They push scientists and engineers to innovate, creating new technologies that not only advance space exploration but could also transform what's possible here on Earth. For example, designing energy systems that can survive Titan's freezing temperatures could lead to breakthroughs in renewable energy storage for cold regions on our own planet. The obstacles aren't merely technical, they're a test of human ingenuity, persistence, and creativity. And as daunting as these challenges are, they set the stage for the remarkable advancements we're about to discuss. From flying drones that can navigate Titan's thick atmosphere to submarines capable of exploring its methane seas, scientists and engineers are developing some of the most innovative solutions to overcome these extreme conditions. And in tackling Titan's mysteries, we're not just reaching for another world, we're redefining the very limits of exploration itself. Traveling to Titan is no small feat. To put it into perspective, Titan orbits Saturn at a staggering 1 billion kilometers away from Earth. That's over 600 million miles through the vast and unforgiving expanse of space. For a spacecraft to make such a journey, it requires not only an extraordinary amount of energy but also propulsion systems that are both highly efficient and capable of sustaining a mission lasting years. This is where breakthrough propulsion technologies come into play, rewriting the rules of interplanetary travel and making missions to distant worlds like Titan a reality. Let's begin with one of the most revolutionary advancements in space propulsion, ion propulsion. Unlike traditional chemical rockets, which burn massive amounts of fuel to produce rapid bursts of thrust, ion propulsion relies on a much more gradual but incredibly efficient process. It works by electrically charging or ionizing a gas like xenon, and then using electromagnetic fields to accelerate those ions out of the engine. This creates a steady, gentle thrust that builds over time. While it doesn't produce the immediate power required to launch a spacecraft from Earth, it's ideal for deep space missions because it uses far less fuel and can operate continuously for years. NASA has already put ion propulsion to the test with the Dawn spacecraft, which successfully traveled to and orbited 2 separate asteroids, demonstrating the potential of this technology for long-distance exploration. Building on this, solar electric propulsion takes the ion engine concept and integrates it with solar power, making it even more sustainable. Solar electric systems use large solar panels to capture energy from the sun, which is then converted into electricity to power ion engines. This approach not only reduces the need for heavy onboard fuel, but also extends a spacecraft's operational lifespan, allowing it to travel farther and carry more scientific instruments. NASA's upcoming Psyche mission, which will journey to a metal-rich asteroid, will serve as another major demonstration of solar electric propulsion. While this technology is most effective closer to the sun where solar energy is abundant, advancements in energy storage and power efficiency could make it a viable option for missions to Titan. However, for missions to the outer solar system where sunlight is much weaker, another promising solution comes into play: nuclear thermal propulsion. This technology has been in development for decades, and it's now beginning to show real promise for deep space exploration. In a nuclear thermal engine, a reactor heats up a propellant, usually liquid hydrogen, which then expands and is expelled to produce thrust. The result is a propulsion system that's far more efficient than chemical rockets, while also generating significantly higher thrust than ion propulsion. This combination of efficiency and power makes nuclear thermal propulsion ideal for missions to Titan, where a spacecraft needs to cover enormous distances yet still arrive within a reasonable time frame. Additionally, the heat generated by the reactor can also be used to power onboard systems, ensuring a steady energy supply even in the distant reaches of the solar system where solar power is no longer practical. And the innovations don't stop there. Engineers are now exploring hybrid systems that combine multiple propulsion methods, such as using chemical rockets for the initial launch and then switching to ion or nuclear thermal propulsion for the long-duration cruise phase. Such systems are designed to balance the need for high thrust early in the mission with the fuel efficiency required for interplanetary travel. These advancements not only make missions to Titan possible, but also pave the way for exploring even more distant destinations like Uranus, Neptune, or beyond. What's truly remarkable about these propulsion technologies isn't just their ability to shrink the vast distances between planets. It's how they enable missions to carry heavier payloads, stay operational for longer periods, and operate more sustainably, all while pushing the boundaries of human ingenuity. With these breakthroughs, we're no longer limited to brief flybys of distant worlds. We can now design missions that linger, explore, and return unprecedented amounts of data. But reaching Titan is only the first step. A journey of 1 billion kilometers through space means nothing if we're not prepared for what comes next. Navigating Titan's unique environment, landing safely, and beginning the exploration of its mysterious and alien surface. This is where the next wave of innovations comes into play, tackling the challenges of operating in one of the most extreme environments in the solar system. Let's take a closer look. Landing on Titan represents one of the most complex engineering challenges in planetary exploration. Titan's atmosphere is a paradox, it's a blessing and a curse. On one hand, the dense atmosphere, which is 4 times thicker than Earth's, provides plenty of drag to slow a spacecraft during descent, potentially making landing softer and safer. On the other hand, this very thickness, combined with Titan's hazy skies and frigid temperatures, makes achieving a controlled and precise landing anything but straightforward. To meet these challenges, engineers have developed revolutionary entry, descent, and landing systems, or EDL systems, tailoring them specifically to Titan's unique environment. Let's first consider the entry phase. When a spacecraft approaches Titan, it must endure extreme speeds as it encounters the Moon's atmosphere. Unlike Earth, where high atmospheric pressure helps dissipate heat during entry, Titan's atmosphere is less familiar territory. A specialized heat shield is essential to protect the spacecraft from burning up as it compresses and heats the dense nitrogen and methane atmosphere. But here's where it gets tricky because Titan's atmosphere is so dense. The design of the heat shield must strike a delicate balance. It needs to withstand the friction and high temperatures of entry, but also slow the spacecraft enough to ensure a stable descent. Engineers achieve this by using materials like reinforced carbon-carbon, specifically designed to handle the thermal stresses of extended atmospheric entry. Once the spacecraft has survived the fiery plunge through Titan's upper atmosphere, the descent phase begins, and this is where Titan's thick skies become both an opportunity and a challenge. For slowing the spacecraft, traditional parachutes are an effective tool, but on Titan, they need to be larger and more robust than anything used on Earth or even Mars. Why? Because the dense atmosphere provides significant drag, but Titan's weaker gravity, just 1/7 that of Earth, means the spacecraft doesn't naturally fall as quickly. This requires parachutes that can both decelerate the spacecraft and maintain stability during the long descent. Engineers often design multi-stage parachute systems, deploying smaller chutes first to slow the vehicle enough to deploy larger main parachutes capable of handling the final descent. These systems are carefully tested under Titan-like conditions on Earth to ensure they perform reliably. But even parachutes alone aren't enough. To land safely on Titan's surface, spacecraft must deal with the unknown uneven terrain, potential winds, and poor visibility caused by the perpetual haze. This is where retro-propulsion systems come into play. These are rocket-like thrusters that fire just before landing to further slow down the spacecraft, giving it a level of precision and control that passive systems like parachutes can't provide. For Titan, these thrusters must be designed to function in cold, methane-rich air, a challenge that requires rigorous testing of materials and fuels. Retro-propulsion also helps reduce the risk of landing too hard on what could be rocky, icy, or even slushy terrain. NASA's Dragonfly mission is perhaps the most exciting example of these technologies coming together. Scheduled to launch later this decade, Dragonfly is not just landing on Titan, it's landing with style. Rather than a traditional rover, Dragonfly is a rotorcraft, a drone equipped with 8 rotors similar to a giant quadcopter. This unique design leverages Titan's dense atmosphere to its advantage. Unlike on Earth or Mars, where flying a rotorcraft requires significant energy due to thin atmospheres, Titan's thick air and low gravity create the perfect conditions for a flying vehicle. Dragonfly will use a heat shield during entry, a parachute to slow its descent, and in a groundbreaking innovation, will switch to powered flight once it's close to the surface. This allows it to not only land softly but also scout for the safest landing site in real time, guided by onboard sensors and cameras. What makes Dragonfly truly groundbreaking is its ability to explore multiple locations across Titan. After landing, it won't be limited to a single site like traditional landers. Instead, it will fly from place to place, covering distances of up to several kilometers in a single flight. This unparalleled mobility allows Dragonfly to investigate a variety of terrains, from the dunes of Titan's equatorial regions to the shores of its methane lakes. Each flight will rely on the same aerodynamic principles that guided its descent, demonstrating how innovative design can transform the way we explore alien worlds. Landing on Titan demands creativity, precision, and resilience. The combination of heat shields, parachutes, and retro-propulsion systems represents the culmination of decades of research, each piece working in harmony to overcome one of the most challenging landing environments in the solar system. And with missions like Dragonfly leading the way, we're not just landing on Titan, we're paving the way for a new era of planetary exploration, where the boundaries of what's possible are continually redefined. Now that we've touched down on Titan, the real adventure begins exploring its alien landscape and unlocking the secrets hidden beneath its icy skies. Enter Dragonfly, a groundbreaking rotorcraft developed by NASA that's set to redefine how we explore other worlds. Dragonfly isn't just another rover or lander. It's a flying laboratory, a fully autonomous multi-rotorcraft designed specifically to navigate Titan's unique and diverse terrain. It represents the next leap in space robotics, combining cutting-edge technology with the adaptability required to thrive in an environment as extreme and unpredictable as Titan. Dragonfly's design is nothing short of revolutionary. Picture a large drone with 8 rotors, resembling an advanced version of the quadcopters you might see zipping around on Earth. But this isn't your standard drone. It's been meticulously engineered to take full advantage of Titan's thick atmosphere and low gravity. In fact, Titan's dense air, almost 4 times thicker than Earth's, makes flying far easier than it would be here or even on Mars. This unique feature allows Dragonfly to soar effortlessly across vast distances, covering hundreds of kilometers during its mission, something no previous space explorer has been capable of achieving. Its mobility on a scale that completely transforms how we think about planetary exploration. What makes Dragonfly even more remarkable is its autonomy. Operating on Titan brings a whole new set of challenges. Given the immense distance between Earth and Saturn, signals take over an hour to travel in one direction. That delay means Dragonfly can't rely on instructions from mission control for every move. Instead, it's equipped with advanced artificial intelligence, enabling it to make decisions on its own. Its onboard systems allow it to assess its surroundings in real time, navigate complex terrains, and even choose the most promising scientific targets, all without waiting for human input. This level of autonomy is crucial for navigating Titan's diverse landscape, which includes everything from vast sand dunes and rocky outcrops to the tantalizing coastlines of its methane lakes. But Dragonfly isn't just about moving from place to place. It's a mobile science lab packed with cutting-edge instruments. Among its tools are spectrometers to analyze the chemical composition of Titan's surface, sensors to detect signs of organic molecules, and even a drill to sample the icy crust. These instruments are designed to probe some of the most fundamental questions about Titan. What is the chemistry of its surface and atmosphere? Could it harbor the building blocks of life? And what does this world tell us about the origins of life itself? By exploring multiple locations, something no stationary lander can do, Dragonfly can gather data across a variety of environments, painting a much clearer picture of Titan's complex and dynamic ecosystem. One of Dragonfly's most exciting targets is the region surrounding a massive impact crater, thought to be rich in organic materials. Impact craters on Titan are rare, and their central role in exposing subsurface material makes them particularly valuable for understanding prebiotic chemistry, the very processes that might have once led to life on Earth. Imagine Dragonfly landing near one of these craters, sampling the exposed material, and giving scientists clues about how life could potentially arise in environments beyond our planet. This isn't just exploration, it's a search for answers to some of humanity's most profound questions. Dragonfly's adaptability is equally impressive. Its ability to fly means it can land, investigate an area, take off, and continue its journey to entirely new locations. This level of mobility opens the door to studying a wider range of Titan's environments, from its towering dunes to the shores of its methane seas, and doing so with unprecedented efficiency. Unlike traditional rovers, which are limited to slow, linear movement, Dragonfly can hop from one scientific target to another, optimizing its time and resources to maximize discoveries. But what's truly groundbreaking about Dragonfly isn't just its technical capabilities, it's what it represents. With its AI-driven autonomy, advanced scientific instruments, and unmatched mobility, Dragonfly is more than a mission to Titan. It's a glimpse into the future of space exploration, where robots are no longer passive tools but intelligent partners capable of adapting to the unknown. In tackling Titan's challenges, Dragonfly is paving the way for even more ambitious missions, not only to other moons like Europa or Enceladus, but also to entirely new frontiers we've yet to imagine. As Dragonfly prepares to launch later this decade, it's hard not to feel a sense of awe for the era we're entering. Titan, with its alien seas and frozen landscapes, has waited billions of years for us to arrive, and with Dragonfly, we're finally ready to meet it. But Dragonfly is just the beginning, a symbol of the technological breakthroughs redefining how we explore not just Titan, but the entire solar system. So, what other innovations will shape the future of surface exploration on distant worlds? Let's take a closer look. One of the biggest challenges for any mission to Titan, or any destination in the outer solar system, is energy. At nearly 1 billion miles away, the Sun is no longer a reliable source of power. In fact, sunlight on Titan is about 100 times dimmer than what we experience on Earth, making traditional solar panels almost useless. This means that missions to Titan require something far more dependable and robust, a power system capable of functioning in the deep cold, through Titan's dense haze and over the course of several years. That's where advanced power technologies like radioisotope thermoelectric generators (RTGS) come into play, an energy solution that has already proven essential in some of the most ambitious space exploration missions. So, what exactly is an RTG, and why is it so vital for Titan exploration? An RTG is a type of power generator that converts heat from the natural radioactive decay of elements like plutonium into electricity. It's a remarkably reliable system because it doesn't rely on external conditions like sunlight or wind. Instead, as the radioactive material inside the RTG gradually decays, it consistently produces heat, which is then converted into electricity using thermocouples devices with no moving parts, ensuring durability and longevity. This consistent energy source is a game-changer for missions to places as far from the Sun as Titan, where extreme cold and long distances demand a power system that can perform without fail for many years. RTGs have a long history of success in space exploration. They powered the Voyager spacecraft, which have been operating for over 4 decades and are still sending back data from the edges of the solar system. They've also enabled groundbreaking missions like the Mars Curiosity and Perseverance rovers, as well as the iconic Cassini spacecraft, which delivered some of the most stunning images of Saturn and its moons, including Titan itself. This track record of reliability in extreme environments makes RTGs the go-to choice for missions like Dragonfly, where other power systems simply wouldn't survive. On Titan, RTGs do more than just power scientific instruments. They're crucial for mission survival. Titan's surface temperature is a frigid minus 290 degrees Fahrenheit, and such extreme cold threatens the functionality of almost every piece of equipment on board a spacecraft. One of the often overlooked benefits of RTGs is their dual role as both a power source and a heat source. The heat generated by the radioactive decay can be used to keep onboard systems, batteries, and even scientific instruments at operational temperatures, essentially acting as a built-in thermal management system. Without this capability, electronics could freeze, batteries could fail, and the mission itself would be at risk. Beyond RTGs, scientists are also exploring other advanced power systems to complement or enhance long-duration missions. For example, advanced energy storage solutions like specially designed batteries are being developed to work in Titan's unique environment. These batteries must function efficiently at cryogenic temperatures, a significant engineering challenge because traditional battery chemistry often breaks down in extreme cold. By combining these batteries with RTGs, missions can store excess energy for high-demand periods, such as during data transmission or scientific experiments, ensuring uninterrupted functionality even under the harshest conditions. Another emerging technology is the potential use of small modular reactors, tiny nuclear reactors designed for space exploration. While still in development, such reactors could provide greater energy output than RTGs, enabling more ambitious missions with heavier scientific payloads or more energy-intensive instruments. Though these reactors are not yet ready for Titan missions, they represent the next frontier in powering deep space exploration and could one day revolutionize how we explore distant worlds. Dependable power systems are the backbone of any long-duration mission, especially on a world as challenging as Titan. They keep scientific instruments running, enable communication with Earth, and most importantly, ensure the survival of the spacecraft in an environment where failure is not an option. Advanced systems like RTGs don't just solve the problem of generating power in the outer solar system. They embody the resilience and ingenuity needed to explore places as remote and extreme as Titan. With these technologies, missions like Dragonfly don't just survive, they thrive, opening the door to years of groundbreaking discoveries on one of the most intriguing moons in our solar system. And as we continue to refine these systems, they'll ensure that humanity's reach into the cosmos extends further than ever before. Exploring Titan isn't just about traveling to a distant moon, it's about unlocking the secrets of its unique environment. To accomplish this, scientists are equipping missions with some of the most advanced and specialized scientific instruments ever developed. These tools are designed to operate in Titan's extreme conditions, gathering crucial data about its thick, nitrogen-rich atmosphere, its icy surface, and the tantalizing possibility of a subsurface ocean that could harbor the ingredients for life. It's like sending a fully loaded laboratory to another world, one capable of detecting everything from complex organic molecules to seismic activity deep beneath the crust. Let's start with a key player in this exploration: spectrometers. These instruments allow scientists to study the composition of Titan's atmosphere and surface with incredible precision, breaking down light into its component wavelengths to identify the chemical makeup of whatever they're observing. Take, for example, the mass spectrometer aboard the upcoming Dragonfly mission. As this flying laboratory navigates Titan's dunes and methane lakes, its spectrometer will analyze atmospheric gases, looking for traces of organic compounds. By doing so, it can reveal how Titan's atmosphere interacts with its surface, potentially identifying molecules that hint at prebiotic chemistry, the early chemical reactions that could lead to life. This isn't just about understanding Titan itself, it's about piecing together a universal puzzle, how life might emerge in conditions radically different from those on Earth. Next, chemical analyzers take the investigation even deeper, examining surface materials for signs of organic complexity. Titan's surface is rich in hydrocarbons, the building blocks of life as we know it, making it an extraordinary site for chemical analysis. Instruments like laser-based chemical analyzers can study samples collected from the ground, vaporizing small quantities of material to identify their composition. For instance, they could detect amino acids or other molecules that play a central role in biology. Combined with data from atmospheric studies, these analyses can help scientists determine whether Titan's unique chemistry mimics early Earth enough to suggest that similar processes could occur elsewhere in the universe. Moving beneath the surface, there's growing excitement about exploring what lies beneath Titan's icy crust. Scientists strongly suspect that Titan harbors a vast subsurface ocean of liquid water mixed with ammonia, a potential haven for simple microbial life. To investigate this hidden world, seismometers play a crucial role. These instruments measure the vibrations and shifts in Titan's surface caused by geological activity, such as the tides created by Saturn's gravitational pull or even possible ice quakes. By studying these vibrations, seismometers help scientists map Titan's internal structure, pinpointing the depth and composition of its subsurface ocean. Such discoveries could reveal whether this ocean contains the energy and chemical environment needed to support life. And let's not forget instruments designed for surface imaging. Titan's dense atmosphere makes it nearly impossible to rely on traditional optical cameras, but radar imagers solve this problem by bouncing radio waves off the surface to create detailed maps. These radar systems can penetrate the haze to reveal features like dune fields, river channels, and the shores of Titan's methane lakes. Tools like these not only help identify safe landing sites, but also guide the mission to areas most likely to yield groundbreaking discoveries. Imagine mapping the intricate coastline of a methane sea, identifying potential landing spots for future underwater probes designed to dive through Titan's alien oceans. What's truly remarkable about these instruments is how they work together as part of a larger scientific ecosystem. For example, data from spectrometers and chemical analyzers can complement seismic readings to paint a more complete picture of Titan's potential habitability. And with each new finding, we get closer to answering profound questions. Can life exist in an environment where water is frozen solid on the surface and methane takes the role of water as a liquid? What can Titan teach us about the early stages of Earth's own evolution? And could similar processes be occurring on other icy moons or even exoplanets beyond our solar system? The discoveries waiting on Titan could reshape our understanding of where and how life could exist in the universe. Instruments capable of detecting the faintest traces of prebiotic chemistry or even microbial life might show us that the conditions for life are far more common than we thought. And if Titan's icy world holds the key to unlocking those answers, the implications extend far beyond one moon orbiting Saturn. They challenge us to rethink what it means for a planet or moon to be alive. This marks a turning point, not just in our journey to understand Titan, but in our quest to find life anywhere it might hide. Next, we'll explore how these groundbreaking discoveries could potentially influence future missions and shape the search for life throughout the cosmos. Exploring Titan requires more than just advanced hardware and robust scientific instruments. It demands intelligence. Not human intelligence in the cockpit, but artificial intelligence guiding the mission every step of the way. With 1 billion kilometers separating Titan from Earth, real-time human control is impossible due to the immense delay in communication, with signals taking more than an hour to make the round trip. That's where AI and machine learning step in, acting as the brain behind autonomous exploration. These technologies allow spacecraft and robotic explorers to make critical decisions independently, adapting to Titan's unpredictable environment while ensuring the success of the mission. One of the most significant roles AI plays in Titan exploration is in managing the spacecraft's onboard decision-making systems. Unlike missions closer to Earth where a ground team can provide constant oversight, Titan's distance requires a high degree of autonomy. AI enables spacecraft to evaluate their surroundings, analyze vast amounts of data, and make real-time adjustments. For example, imagine Dragonfly, the upcoming rotorcraft mission to Titan, encountering unexpected weather changes, perhaps strong winds sweeping across a methane lake or shifting dunes of frozen hydrocarbons. With its AI-driven navigation system, Dragonfly can instantly assess its situation, adjust its flight path, and stabilize its course without waiting for instructions from Earth. This kind of adaptability is essential for thriving in Titan's dynamic and often unpredictable conditions. Machine learning takes this autonomy to the next level by allowing Titan's explorers to learn from their experiences and improve over time. These systems are trained on massive datasets, everything from terrain patterns to atmospheric simulations before even leaving Earth. Once on Titan, they can compare their collected data to this training, identifying features or phenomena that match known patterns while flagging anomalies for further investigation. For example, if Dragonfly's onboard systems detect a surface feature that doesn't align with what it was trained to expect, it can prioritize that area for further study or alert Earth-based scientists for deeper analysis. This ensures that no critical discovery is overlooked, even in an environment as alien as Titan. AI also plays a crucial role in scientific data analysis. In an environment as rich and complex as Titan, the amount of data generated by instruments is staggering. AI-driven systems onboard can sort through this data at incredible speeds, identifying key patterns, correlations, or anomalies that might indicate something significant, like unusual concentrations of organic molecules or seismic activity hinting at a subsurface ocean. By processing this information on site, AI reduces the need to send massive amounts of raw data back to Earth, saving precious energy and bandwidth while giving scientists more actionable insights in near real time. Predictive modeling is another game-changing application of AI in Titan exploration. Using advanced algorithms, spacecraft can predict environmental conditions like wind patterns, atmospheric density changes, or even the stability of a potential landing site. This capability allows missions not only to avoid potential hazards but also to optimize their exploration strategies. For instance, by predicting the best conditions for flying, Dragonfly can plan its flights to maximize safety and efficiency, ensuring it can cover more ground and collect more valuable data. But AI's role isn't just limited to autonomous decision-making and data processing, it also works hand in hand with Earth-based scientists. AI technologies act as a bridge, ensuring that discoveries made millions of miles away are presented in an intuitive and actionable way. By analyzing data before transmitting it back to Earth, AI can highlight the most important findings, enabling scientists to focus on what really matters without being overwhelmed by raw information. This symbiotic relationship between human researchers and AI ensures that the mission stays focused, efficient, and productive, even with the challenges posed by Titan's immense distance. A great example of AI in action can be seen in past missions like the Mars rovers. These rovers use AI-driven navigation systems to autonomously avoid obstacles and choose the most efficient paths across Martian terrain. Now, those same principles are being scaled up and enhanced for Titan's far more complex environment. Dragonfly, for instance, will rely on similar systems to navigate both in the air and on the ground, adapting to challenges that were impossible to predict during its pre-launch phase. In essence, AI and machine learning are the unsung heroes of deep space exploration. They allow us to push the boundaries of what's possible, enabling missions to operate independently, discover efficiently, and adapt intelligently. Without these technologies, exploring Titan's methane-coated lakes, icy dunes, and hazy skies would be an overwhelming and often impractical task. But with AI as our partner, we're not just reaching Titan, we're thriving there, one autonomous decision at a time. This is the future of space exploration, where human ingenuity meets machine precision to uncover the mysteries of worlds far beyond our own. Titan stands as the ultimate challenge for human exploration, a world so alien, yet so tantalizingly familiar that it could forever change how we see our place in the universe. Its dense atmosphere, freezing temperatures, and methane-filled lakes create one of the most extreme environments in the solar system, demanding extraordinary innovation just to land, let alone explore. But these challenges are exactly what make Titan such an unparalleled destination. The technologies being developed to reach and study this distant moon are not just advancing space exploration, they're redefining what's possible both beyond Earth and here at home. Our journey to Titan starts with cutting-edge propulsion systems like ion and nuclear thermal engines, which allow spacecraft to cross the billion-kilometer distance between Earth and Saturn more efficiently than ever before. These advancements aren't just about reaching farther, they're about traveling smarter, carrying more scientific payloads, and unlocking extended missions to even more distant worlds. Once there, entry systems designed to navigate Titan's dense atmosphere ensure that every spacecraft can descend safely, combining robust heat shields, adaptive parachutes, and precision retropropulsion to master an environment unlike any other. On the surface, robotic explorers like NASA's Dragonfly mission are breaking boundaries. This flying laboratory, designed to harness Titan's thick atmosphere and low gravity, will leap from site to site, studying everything from organic rich dunes to the edges of methane seas. Its ability to autonomously navigate, collect samples, and conduct experiments reflects how far we've come in designing machines that are as adaptable as the worlds they explore. Supporting Dragonfly and missions like it are advanced power systems, such as radioisotope thermoelectric generators, which keep instruments running and systems warm in Titan's frigid environment. These same technologies could one day revolutionize energy solutions for remote regions on Earth, offering sustainable power where it's needed most, and at the heart of it all is artificial intelligence. Without AI, exploring Titan would be impossible. From autonomously guiding spacecraft and drones to analyzing vast amounts of scientific data, these systems act as our eyes, ears, and even decision makers in environments where human presence is far beyond reach. Every decision made by an AI-driven explorer on Titan brings us one step closer to unraveling the mystery of whether life, or its precursors, could exist on such an alien world. And the implications extend far beyond Titan itself. The lessons learned here will inform how we explore other icy moons like Europa or Enceladus, and even exoplanets in distant star systems. But the rewards of Titan exploration aren't limited to space. The technologies we're developing, high-efficiency power systems, groundbreaking robotics, and advanced AI, have applications that could transform life on Earth. Whether it's providing renewable energy in extreme climates, designing AI systems to assist in disaster response, or building autonomous drones to explore our own planet's most remote regions, the innovations born from Titan missions are already shaping a better future for humanity. Titan is more than a scientific target. It's a testament to human curiosity, resilience, and ingenuity. It challenges us to dream bigger and to solve problems we've never faced before. And as we prepare for missions like Dragonfly, we're reminded that exploration is not just about answering questions, it's about inspiring the next generation of explorers to continue pushing boundaries, whether here on Earth or across the vastness of space. So, what do you think Titan could teach us about life, our universe, or even ourselves? Share your thoughts in the comments below. Your voice is a part of this journey too. And if you're as excited as we are about exploring the cosmos, don't forget to like, share, and subscribe to stay connected. Together, we'll continue to push the limits of what's possible and uncover the incredible mysteries of our universe. This is just the beginning.